So from the point of view of vector addition and scalar multiplication, vector spaces are basically the same thing as n space, Rn. And we did, take a look at some examples in the previous sections. We had Rn itself, then we look at the space of functions at, from a domain, a closed bounded interval to the reals. We looked at functions from the reals to the reals. We looked at matrices. Each of those satisfies the 10 axioms, assuming we define the vector sum and the scalar multiplication as we had for, the specific examples. But we did see an example that was slightly different from the other ones, right? That line V, where the second coordinate was twice as big as the first coordinate, and it resided in R2, and it went through the origin. That's not Rn. I mean, even though it looks like a copy of R, if you look at it straight on, it's not Rn, it's not R, it's something that lives or resides inside of R2. In general, most of the spaces that will be of interest to us will reside inside of some basic vector spaces. So if V is a vector space and W is any subset of that vector space, if it turns out that it is a vector space, when you endow it with the same addition and multiplication, scalar multiplication, as the one that was found in V, in other words, if it's closed under addition, it's closed under scalar multiplication, and if 0 is part of W, then W is a subspace or a space in its own right, which we call a subspace. So the line here, which I've called W, previously I had called it V, which is the straight line through the origin where the second coordinate is twice as big as the first. That's a subspace of R2. And we'll denote that in general by W smaller than V. We should, to be fair, probably call it smaller than or equal to V, because if I just write smaller than, it makes it look as though it could never be equal. But as we'll see, V is a subspace of itself, and so we'd like to have this sort of equality being at least included in the options. We don't. We'll just write smaller than. It's not a smaller than, which is the same smaller than when we say that 0 is smaller than 3. It's a different smaller than. We just use the same notation. This is not a universal notation. You might not actually see it in other textbooks. For those of you who will study more advanced mathematics, it's notation that's borrowed from the idea that a subset of a group could be a subgroup. That's the same sort of idea, and so I borrowed the same notation. There's a very straightforward test that allows us to tell if a subset of a vector space, subset W of a vector space V, is actually a subspace. We only need to check 3 conditions, not the 10 conditions. That is because V is a vector space and a lot of the other conditions are automatically satisfied. So if we already know that W is a subset of n space, a subset of matrices, a subset of functions, then all we need to verify are these 3 things. We need to verify that whatever plays the role of the 0 vector is in the subset W. We need to show that W is closed under addition. If you give me 2 vectors, U and V, general vectors here, not specific vectors, they're in W, then their sum is a vector which is also in W. Hence, you cannot leave W by just adding together vectors in W. And you only need to show, thirdly, that the W is closed under scalar multiplication. If you give me a vector U and a scalar, when I multiply U by R, I get a new vector which is itself also in W. In other words, that 0 is in the subset to start with, and that any linear combination of vectors in the subset stays in the subset. That's the subspace test. I'll give you a bunch of examples here where we apply it, the subspace test, and we see whether something is a subspace or potentially if it's not an actual subspace. So here's a subset of R3. So T consists of a bunch of vectors in R3. So this is telling us that all of the U vectors in question will look like triple x, y, z. That's the general form. The constraint, the condition to be in T is that the inner product of U with 1, 2, 3 should be equal to 0. Now that's not true of every vector in R3. There are vectors, such as for instance the vector 1, 2, 3 itself. If you do the inner product or the dot product of 1, 2, 3 with itself, you do not get 0. So T is not the entirety of R3. And this is what this message says, what this little symbol says. It says that T is a subset of R3, but it is not R3 in its entirety. There are things in R3 that are not in T. If we wanted to know specifically what it looks like, well, we can just sort of simplify or work with the membership condition, right? U is vector x, y, z. 1, 2, 3 here gets repeated as 1, 2, 3, and you do the actual dot product that's supposed to equal to 0. The dot product of x, y, z with 1, 2, 3 is actually this expression right here. So T is in fact a plane in R3. It's the plane x plus 2y plus 3z is equal to 0. Now, as long as you understand, and I mean truly understand, what it means for a vector to be part of a set, for U to be part of T, for V to be part of W, whatever your set is, if you really understand what that means, then the subspace test is easy to apply. If you don't understand what it means for a vector or an object to be part of a set, you're straight up not going to have a good time trying to use the subspace test. But that's true in general of mathematics. You need to understand what it means for an object to be part of a set. The first question you ask in the subspace test is the 0 vector in the set in question. Well, how would we know if 0 is in the set? The membership condition is that 0.123 should give us 0. But that's indeed the case, right? If you replace U by 0, 0, 0 here, you're going to get 0 times 1 plus 0 times 2 plus 0 times 3. Yeah, that is 0. So the 0 vector satisfies the membership condition, hence 0 is in the set T. Is T closed under addition? I remind you, you do not want to just test it out with specific vectors in T, especially here since we don't really know a vector in T. Oh, we know 0, 0, 0s in T, but that's not a very interesting vector, is it? We want to show that if we have random U and V in T, then U plus V, their sum should also be in T, or potentially not in T, in which case then the subspace test fails. So what do we know if U and V are in T? We know that U dot 1, 2, 3 is 0, and we know that V dot 1, 2, 3 is 0. That is just a rewriting of this condition right here. So, okay, so now we have a mathematical formulation to tell us that U and V are in T. And we want to show, assuming that we think it's a subspace and that the subspace test will apply, we want to show that the sum U plus V is itself in T. And what does it mean for U plus V to be in T? It means that the dot product of U plus V with 1, 2, 3 should give us 0. So this is what we want to show, and we'll show it using the hypotheses, the assumptions, which are here. If when you show the conclusion is true, you don't end up using the hypotheses, there's a good chance that you've muffed something up. Right? You should be using these hypotheses, these assumptions, to show the conclusion is true. Otherwise, there's no link between the hypothesis and the conclusion. Now, that happens every once in a while, but in general, that's not going to be the case. So it's easy to show that u plus v dot 1, 2, 3 is 0. We just use the properties of the dot product and the sum of vectors. U plus v dot 1, 2, 3, that's the same thing as u times 1, 2, 3 plus v times 1, 2, 3. When I say times here, I mean the dot product. Okay, so I can break this down as a sum. What do I know about u dot 1, 2, 3 and v dot 1, 2, 3? Well, by hypothesis, both of these were 0 because I assumed that u and v were in t to start with. So this is 0, this is 0, and the sum of 0 and 0 is 0. So the condition for u plus v to be in the set T applies to u plus v, so u plus v is in T. And the only thing we used here to show that u plus v was in T was that u and v were both in T. Now the next time around, you'll have a different T or a different set, and the membership condition will be different. So you can't reuse exactly that thing. This applies to this specific set T. But the principle is the same. The next bit we ask, is T closed under multiplication by scalars? If you start with a scalar r and you have a vector u, then what do you know? You know that u dot 1, 2, 3 is equal to 0. That's the condition for u to be in T. We don't know anything about r except that it's a real number. Now you'd like to be able to show, using the condition that u dot 1, 2, 3 is 0, that ru is in T, which means to say that ru dot 1, 2, 3 should be equal to 0. But what's ru times 1, 2, 3? By the rules of the inner product in R3, ru dot 1, 2, 3 is the same as r times u dot 1, 2, 3. And u dot 1, 2, 3 by construction, that's 0. I mean, that's what we've assumed here when we assumed that u was in T to start with. So this bit is 0. So r times 0 is 0. Now when I write r times 0 here, the times that is here is just there because otherwise r and a 0 next to it would look funny. And if I put a dot next to it, you might think it's meant to be a dot product. The x isn't the cross product from the previous chapter, it's just a way to say multiplication, normal multiplication of two real numbers. So okay, ru dot 1, 2, 3 is equal to 0, and that means that ru as a vector, which is the vector u that's been stretched by r, is also in T. And so we've met the three conditions. The 0 vector was in T, right here. T was closed under addition, and T is closed under multiplication by scalars. And then we conclude then that T must be a subspace of R3. We didn't exhibit any vectors in T apart from the 0 vector, and yet we've shown that T is a subspace. This plane is a subspace. The fact that 0 is in T, in this specific case here, tells us that this plane is a plane through the origin. Now, the thing about planes in R3 is that they can always be written in the point normal way, right? Any plane in R3 can be written this way. What this example shows us is that if d is equal to 0, if this is 0, then the corresponding plane is going to be a subspace. Because none of what we've done here really depended on the normal vector being exactly 1, 2, 3. We could have had just a regular n throughout, and the results would have been the same. The proof would have been the same. Right? The only thing that mattered is that in the condition, we had that u dot, the normal vector, was 0, and that v dot, the normal vector, was 0. U dot normal vector is 0. But if something here was different than 0, then no, we wouldn't have had a subspace. Any plane through the origin in R3 is a subspace of R3. And the same sort of example would have shown us that any plane in R3 which doesn't go through the origin cannot be a subspace of R3. In particular because 0, the vector 0, would not be in the plane or on the plane. Well, what can we say about lines? Planes through the origin are vectors in R3. In fact, a plane, however you define that goes through the origin in Rn is a subspace. Any hyperplane that goes through the origin in Rn would be a subspace. That also applies to lines. So we'll show here that a line in Rn is a subspace of Rn, assuming that the line goes through the origin. So the example here is the set L. It's a subset of Rn because everything in L looks like T times V. T is a real number, and V is some vector in Rn that's been selected. That's basically the direction vector for the line. So T times V, you take your vector V and then you stretch it and scale it using all the possible scaling factors. You reverse it with negative scalars and you stretch it. You get all possible points on the line. Is it the case that L is a subspace of Rn? Like, we know that L is a subset of Rn, that's for sure. That's by construction. Everything in L is a vector in Rn. The question isn't whether it's a subset or not. The question is it a subspace? Does it satisfy the additional properties to be a vector space? So we just need to apply the subspace test. We need to verify if the 0 vector is in L. Well, again, this is going to be easy if we understand what it means for something to be in L. If 0 is in L, it means that you should be able to write 0, the 0 vector here. I could put an arrow just to really distinguish them, but it's the bold font. We should be able to write it as T times V for some T in R. Yes, we can. I just need to take T is equal to 0. And if T is equal to 0, then 0 times V, that is of the form T times V, hence it is in L, and it's exactly equal to 0, the 0 vector. So yeah, the 0 vector is in L. I'd like to know now whether if I take two vectors in L, their sum is also in L. Okay, what does it mean for two vectors to be in L? Usually what I write here is like, okay, let's U be in L and V be in L, and that's not a great notation because V in this case is being co-opted as the direction vector. What the subspace test really says, right, if you have two things in L, their sum is also in L. So let's take two things in L. What do two things in L look like? It's going to look like TV and SV, where T and S could conceivably be the same thing, but they could also be different. So these are two members, two elements of the set L. Their sum is also a vector, but the key question is their sum a vector that happens to reside or lie in L? And what does it take for something to be in L? You need to be able to write it as a scalar times V, whatever that specific V here is. Even though it's unknown, it's fixed, it's specific. It's not a variable there. So let's add our two vectors in L, TV plus SV. That becomes, by the rules of scalar multiplication, T plus S times V. T is a real number. S is a real number. Their sum is also a real number. Let me call it K. And so the sum of TV and SV is KV. KV satisfies the membership condition. KV is a scalar times the vector V. So yeah, it is an L. The last thing we need to verify is that if something is in L and we stretch it or we scale it, then the resulting vector is also going to be in L. Well, so what's something in L? It's something that looks like t times v for some t. When I write it like this here, I'm talking about a specific t, although it is unknown. When I write it inside of the curly brackets, I'm talking about all the tv's. So if I have a vector in L and I stretch it or scale it by a factor r, the new result will be r times tv. That is a vector for sure. The question is, okay, it's an Rn, is it also in L? And what does it take to be in L? It needs to be written as a scalar, some real number times v. But sure enough, r times tv is the same thing as rt times v. Rt is a real number. And so I have here something in the reals times the vector v. Yeah, that is an L. So the three subspace test conditions are satisfied. The line L, which is a line in Rn through the origin with direction vector v, is a subspace of Rn. And we can conclude, right, because we didn't specify anything about v here, just that it was known and fixed. Any line that goes through the origin in Rn is a subspace of Rn, and any line in Rn which does not go through the origin is not a subspace of Rn. Because it would fail the subspace test, the zero vector would not be in it. Here's an example that is going to be a little bit more useful. Perhaps not so much in this course, although we will see polynomials again in the future, but for the more advanced courses and the applications. So we start with a vector space, which is the function space. It's all the functions from R to R. What's a vector in that space? A function from R to R. Sine of x, for instance, would be a vector in that space. P is going to be a subset of all of these functions. We're not going to look at functions like sine of x. We're going to look only at polynomials. Polynomial is something that can be written as a0 plus a1x plus a2x squared and so on, all the way up to anx to the power n. The ai's are going to be some real numbers, and n has got to be some integer greater than or equal to 0. So anything that looks like this is a polynomial. X squared plus 1 is a polynomial. X to the power 3023 minus x is also a polynomial. Well, there's infinitely many of them, but in fact there's a lot less, or a lot fewer of them than you would have regular functions. But that's topic for another course. Is it a vector space? Well, it would be a vector space if the zero function is a polynomial, if the sum of two polynomials is a polynomial, and if, when I scale a polynomial, the result is itself a polynomial. Now, adding two polynomials and multiplying a polynomial by a scalar is what you would do like with regular functions, right? You add two functions by adding their output at every single x. You do the same thing for polynomials, and so on, and similarly with the multiplication by a scalar. So, is 0 in P? Sure, in P the zero vector is that special function, the zero polynomial, which here I write 0 with a little x to remind us it's a polynomial, and that's the polynomial that's always equal to 0. It's not a super interesting polynomial, but it definitely satisfies the condition to be a polynomial, right? It's something of the form a0 plus nothing else, so n is equal to 0, and a0 is 0, which is itself a real number. So the zero polynomial, the thing which is identically 0, is a member of the set of all polynomials. Is the set P closed under addition? I claim that it is, and that it's obvious the sum of two polynomials is a polynomial. There's a formal argument here that basically says as if px is a polynomial of degree n, assuming n is greater than 0 and all the coefficients are real, and qx is a polynomial of degree m, where m is greater than n, again all of the coefficients are real, then px plus qx would be this sort of monster there. For powers up to n, you'd be adding the coefficients together, and for powers between n plus 1 and m, you just have the coefficients of q. But you might say, well, I don't know, what if it's the other way around? What if it's n greater than m? So sure, no problem, just relabel them. The result here is still a polynomial. Make you notice something. I say greater than rather than greater than or equal to. I mean, I have written here greater than or equal to, and we get sort of tired of saying greater than or equal to. So from the context, sometimes greater than actually means greater than or equal to. Sometimes it just means strictly greater. When I want to specify that it couldn't be equal to, I'll usually, although not always, say that something is strictly greater than. Okay? But what matters is what I've written down most of the time, not so much the shortcuts that all mathematicians sort of take, because we understand from the context what it's supposed to mean. And is it closed under scalar multiplication? Sure, you'd multiply a polynomial by a scalar. You can't sort of create a new sin x term in there. It's impossible, right? You're just multiplying coefficients by some scalar. Possibly the scalar is 0, in which case you've created the 0 function, but that's not a problem because the 0 function is a polynomial. So here's the formal proof, if you want, formal description of what we just said there. The set of polynomials is indeed a subspace of the set of functions from R to R. In other words, 0 is a polynomial. The polynomial that's always 0, no matter what the value of x is. And if you do linear combinations of polynomials, it is impossible for you to exit the world of polynomials. I say that, but I should add a restriction. If you do finite linear combinations of polynomials, you cannot escape the world of polynomials. If you're allowed to have infinitely many polynomials, it is conceivable, although not necessary, that the end result will not be a polynomial anymore. When you study calculus, you will hear or learn about Taylor functions, Fourier functions, or Fourier representations of a function. For instance, sin at x can be written as an infinite polynomial, x minus x cubed to the power 3 factorial plus x5 divided by 5 factorial minus x to the 7 factorial, and so on. That's a polynomial of infinite degree. And we call that a series representation of a function. Not something we'll study in linear algebra, but remember, when we're talking about linear combinations, we are talking about finite combinations. You're not combining together an infinite number of terms. Transpose of a matrix is obtained by just replacing the rows by the columns and vice versa. So if you start with an m by n matrix A, its transpose is going to be AT, or A transpose. It's going to be an n by m matrix. And the rows of A transpose are the columns of A. In the space of 2 by 2 matrices, the transpose would be given as follows. The transpose of A, B, C, D, written or read column by column, would be ACBD. Written, or I said read column by column, I meant read row by row, my apologies, would be ACBD, read row by row. So here the rows of A, B, C, D becomes the column of the transpose. First row is the first column, second row is the second column of the transpose. So we're going to revisit these a little bit later when we talk about matrices in general, but we have an example here. So I'm going to look at the set S. S is a subset of the 2 by 2 matrices. Everything that belongs to S has to be at the very least a 2 by 2 matrix. So there's no polynomial in S, there's no function in S, there's no triple or 5 tuple or anything other than 2 by 2 matrices. There's not even 3 by 3 matrices. No, it's only 2 by 2 matrices. So it looks like A, B, C, D. So that's the basic form that it has to have. The specific membership condition, the restriction is that the transpose should be equal to itself. So that's a set of matrices. We don't know if it's empty or not. It could be that there's no matrix that satisfies this condition. So it could conceivably be empty. So we'll have to verify that in a second, whether it's empty or not. But the question is it a vector space? Well, the first thing we could try is to verify if the zero matrix, the 0, 0, 0, 0 matrix is in there. And sure, we could do that. But before we get carried away with things, it might be useful for us to have a better description of the set S. Right now, S is written using like letters for matrices. But we know that these are 2 by 2 matrices, so we know that S looks like a set of square arrays, A, B, C, D, where the transpose should be equal to itself. That's the condition. All I've really done here is I've replaced A by A, B, C, D. It's like, okay, well, why am I doing this? If I write this properly, I can simplify the condition a little bit. I can compute directly here on the left-hand side of the equality what the transpose of A, B, C, D is, right? I transpose the rows for the columns. So the first row of A, B, C, D becomes the first column of the transpose, and the second row becomes the second column. So, okay, I'm looking for all the matrices A, B, C, D where, and then this is the membership condition, where A is equal to A, where D is equal to D. That's not really useful because A is always equal to A and D is always equal to D. They're the same things. But where also C is equal to B and B is equal to C. So in fact, this is the membership condition. We're looking for all the matrices A, B, C, D where B and C are the same. Another way to write this, if B is equal to C, well, I write my matrix A, B, C, D, A, B. Oh, I have C, but I know that C is equal to B. So let me just put it in as B, D. So I'm looking for the matrices where the elements on the counter diagonal are the same. They're identical. This would be the set of matrices where the transpose is equal to itself, at least as a subset of 2 by 2 matrices. If I had 5 by 5 matrices, the condition for membership would be different. So now, we have 3 questions to ask about the set, if we think it's a subspace of the set of 2 by 2 matrices. Is the 0 vector in there? Is the sum of 2 vectors in there still a vector in there? And is the scaling or stretching of a vector in there still a vector in there? What's the 0 vector? It's the 0 matrix, the 2 by 2 matrix. Is it the case then that the 0 matrix takes the form A, B, B, D for some A, B, D real numbers? Yeah. If I pick A is equal to 0, B is equal to 0, and D is equal to 0, and I replace that in my membership condition, I'm going to get 0, 0, 0, 0. So sure enough, the 0 matrix is in there because it satisfies the membership condition. The membership condition being that the 2 counter diagonal entries should be the same. What about if I take two vectors in S? Well, a vector in S is a matrix in S where the two counter diagonal entries are the same. Here's another one. They're the same. If I add them together, I'm going to get A plus A prime, B plus B prime, B plus B prime, D plus D prime. And I'd like to know if this result here of two vectors in S is also in S. I need to verify if it is indeed the case that the elements on the counter diagonal are the same. Well, yeah, B plus B prime is equal to B plus B prime. So for sure, it is an S. And I do the same thing for scalar multiplication. I take some arbitrary matrix in S. It's going to have to look like A, B, B, D. That's the only thing that I know. Multiply by K. I get Ka, Kb, Kb, Kd. Is it the case that these two things are equal? Yep. So the subspace test is satisfied, and so this set S of symmetric matrices in M22 is in fact a subspace of M22. I'm going to point something out to you here. When I write things like this, it looks as though there's three values that are really important. And that's the formal and, to be fair, correct way of doing this. It's going to be super helpful for us down the road when we're trying to find bases for these things. But it's not the only way to look at the information. I could just look at this as basically saying, look, S is the set of everything where I have some elements, I don't care what, but these two things have to be the same. So when I pick two arbitrary matrices, I don't really need to care. I could have this here, I could have this here, I could have this here, I could have this here. This would be this would be this. And the only thing that matters really is the equality of these things. So there are some ways to really like hone in on what's important. So you might be comfortable taking the shortcut, but I need to remind you, if you're going to be using the shortcut, I should warn you, I should say, that way lies the chance to make confusing mistakes when we start talking about the dimension of a subspace and finding bases for subspaces.